Hi there, I'm Dr. McFerrin from DM Explains. In this video, I'm going to be talking about MOSFET amplifiers. I'm going to start with the common source amplifier. It is the most commonly seen discrete amplifier configuration. And in the common source amplifier, I have an input signal, Vsig, connected to ground through an input resistor, Rsig. This is my signal source. It's a two-terminal source, and I know that any two-terminal circuit that's linear can be represented using a voltage source with series resistor. And then I have a terminal connection here where I've got V gate to source. And then I have my MOSFET. I'm going into the gate of the MOSFET. The source is connected to ground since it is common source. This is an NMOS MOSFET. And then this is connected from the drain directly to a drain resistor, RD, and I look at the output there. I have an input resistance measured looking into the input terminals, and I have an output resistance measured looking at the output terminals. When we use the small signal model, specifically the pi small signal model, this looks like Vsig, my AC signal source, Rsig, and then I have an open where I measure V gate to source, which is equal to my input voltage. And then across the way from it, I have a dependent current source pointing downwards, which has a value GM VGS. That's connected in parallel with RD, my drain resistor. If I look at Rn, since there's an open circuit here, the input resistance is infinity, and R naught, looking back through the output terminals, is just equal to RD. Vi is equal to V sig, which is equal to V gate to source, because with an infinite resistance across there, 100% of the voltage is dissipated across there. V out is equal to negative GM RD VGS, and we call AV naught, the gain, negative GM RD. This is the gain V naught over Vn. If I add a load resistance then across the drain, then I get AV. AV is equal to AV naught times RL over RL plus RD, which is the same as negative GM RD in parallel with RL. And so that is the same as V naught over Vn as long as I have a load resistance there. The total overall voltage gain, GV, which is defined as V naught over V sig from the signal source to the output, is then equal to negative GM RD in parallel with RL. So the things that I've gotten here are the gains, AV, AV naught, GV, as well as the output and input resistances. For a common gate amplifier, we could work through that whole derivation exercise, but that's probably more than we need to do right now. I know that Rn is 1 over GM, R naught is equal to RD, a V naught, which is V naught over Vn, is equal to GM RD, and a V is equal to positive GM RD in parallel with RL, and GV is equal to RD in parallel with RL over 1 over GM plus R sig. As a reminder, the way that a common gate amplifier looks is that I've got my signal source, but instead of being connected to the gate, it's connected to the source. So I've got V sig. I'll connect it this way. So here is my Vn. The gate is connected to ground, and then I connect the output across the drain. So I measure V naught there. And so the input resistance Rn is here and R0 is measured there. Some brief notes about this amplifier is that Rn is small, which means that this type of amplifier is bad if used alone, because a lot of the times what we're looking for is a large input resistance and small output resistance. But some benefits of this is that it has good high frequency response, which makes it good for radio frequency applications. And typically what we can do is we can match it up or pair it with a common source amplifier to improve upon some of those issues. There's only one other type of amplifier to discuss, and that is the source follower. The source follower, or common drain amplifier, is also sometimes called a buffer, and its characteristics are that Rn is infinite, a V0 ideally is 1, a V is equal to RL over RL plus 1 over GM. The output resistance is 1 over GM, and GV is equal to AV. So those are the characteristics of this. Let's talk briefly about real amplifiers. In a real amplifier, we add an AC ground. This is a signal ground with a bypass capacitor, CS, across any source resistance that I have, RS. I also will include CC1 and CC2 as coupling capacitors. And the reason that those are there is to block the DC signal, the biasing that happens inside of my bias circuit at the input and output. That's the purpose of those. So for example, let's look at a CS amplifier. It may look like this. I've got V sig connected to R sig, and then that's connected through a coupling capacitor, CC1, and I've got maybe RG1, RG2. This is a voltage divider bias connected to my gate, and then I've got VDD up here. That's the voltage source. This is RD, and then here I've got RS to ground, and then I have a bypass capacitor, CS, and then out from the drain I have my second coupling capacitor to the actual output where I would connect my R0, and so that would be where V0 gets measured. So in this circuit, if I look at those capacitors as blocking DC, I look at the biasing part by ignoring the stuff outside of those capacitors. And so I've got VDD, which is a DC voltage source, and then I have my voltage divider bias, RG2 here. I've got my MOSFET. This goes through RD, and this goes through RS. And these are used to set the values of ID and V-gate to source to ensure that the MOSFET is in operation. The small signal model of this looks like this. I've got V sig again, I've got R sig, and then I've got R gate 1 in parallel with R gate 2. We typically make these very large so that way the input resistance is also large. This is VGS here. If I note, my input resistance is measured looking at the parallel combination of R gate 1 with R gate 2. Sounds like Stargate. I think that's the one where like they warp around ancient Egypt or something. I don't know. There's a board game like that. It's called Comet. I haven't played it, but it does look super neat. It's very rare that I haven't played a board game. Then I have over here in the sort of output stage circuit, I've got GMVGS. That's a dependent current source pointing down. I have an equivalent output for this transistor, R0. And then I've got RD in parallel with RL. and that's where I measure V0. The output resistance of this amplifier is seen with the load detached, looking back through the output terminals, and R0 is equal to RD in parallel with little r0. Often little r0 is a lot bigger than RD, and so RD tends to dominate this expression. Then I can point out that Vn, which is V gate to source, is equal to V sig times the parallel combination of RG1 and RG2 over RG1 in parallel with RG2 plus R sig, which is the same as saying it's V sig times R input over R input plus R sig. So if the input resistance is large, then most of the actual input signal makes it to the MOSFET, the amplifier itself. V0 is equal to negative GM VGS RD in parallel with RL in parallel with R0. GV is equal to V0 over V sig, which is equal to V0 over V gate to source times V gate to source over V sig, and it's equal to negative Rn over Rn plus R sig times GM times RD in parallel with RL in parallel with R0. And this arises just by taking the V0 expression over VGS and then taking VGS over V sig from the previous expression. And that's exactly how I arrive at the overall voltage gain. At this point, that's where I'd like to end it for today. In the next video, what I'll talk about is a bunch of examples of analyzing and designing MOSFET amplifiers. That's all for now. Thanks so much for watching. Tap, tap, tap. Bonus tap. Nope. Farts. Why can't I not speak? This is really frustrating today.